Where did life originate from? The first biomolecule was both the carrier of genetic information and an enzyme itself. Welcome to the RNA world, where everything was possible.
In this world, small liposomes emerged, and in this way, the first cells were created.
RNAs had a double role back then. They could reproduce themselves, but they could also act as enzymes, or what we call ribozymes.
The RNA world gave its place to the central dogma of biology, and RNA became the carrier of genetic information, from DNA to protein.
What if we could reverse the order of evolution? Could we create versatile and powerful RNA tools to give new solutions to old problems?
The answer has been given in the form of a new kind of oligonucleotides with a double function called aptazymes.
First, they have an aptamer part, which combines specifically to a molecule of our choice, just like antibodies do. Then, they have a ribozyme part, which is enabled when the aptamer binds to our desired target molecule and carries out a specific task.
The size of aptamers is many times smaller than that of antibodies, so they have a huge potential in the improvement of laboratory techniques, as medical diagnostics, or even as therapeutics. They also have very low antigenicity and can access remote areas, for example, beyond the blood-brain barrier.
Why aren't they more commonly used then?
Aptamers are produced with a method called SELEX, systematic evolution of ligands by exponential enrichment. It is a time-consuming and very expensive method, so we aim to change that.
Synthetic biology has given us the ability to engineer living organisms with new functions. Could we take advantage of the inherent characteristics of life in order to create a platform for natural aptazyme production? And is there a greater force in nature than the one of evolution itself?
We have coupled the fitness of survival of our bacteria with their ability to create optimal aptazymes, that is, with a high binding affinity for any target molecule we want. Using simple words, when the cell produces an aptamer that works well, it survives. Otherwise, it dies. Survival of the fittest aptamer, as Darwin once said apparently.
However, this may still sound tedious considering the randomness of the initial aptamer sequence. Modern technology could give us a helping hand. It is possible, using proper bioinformatics software, to predict the binding sequence of an aptamer, inserting as input our target molecule. This is the in silico part of our project.
Considering the implementation of both in vivo and in silico techniques, we named this innovative method MEDEA, Machine-Enhanced Directed Evolution of Aptamers, referring to the Greek mythical sorceress MEDEA. However, instead of magic, we will be using a self-developed protocol, SELEX, which will be available to anyone all around the globe.
Our system may be simple, but our vision is much broader. We hope to give scientists open and easy access to state-of-the-art technology. Our experience has taught us that there is always a way if you think and work hard, and we plan to use this experience to create a wide range of new possibilities. In other words, we find beauty in simplicity.